So I'm sort of representing Michigan Tech, and I'm in effect the moderator for the evening. And so I'm going to start things off just by saying that our speaker today needs no introduction. And the reason he needs no introduction is he's going to introduce himself, because much of his talk is about how he came to Michigan Tech and where that led him in his career. But since I am the moderator, I'll kick it off by asking you a question, and the answer to the question is going to be the first part of the talk. And so the question is how did you come to Michigan Tech? How did you come to electrical engineering, and what did Michigan Tech do for you as you began your career? And I think I know exactly what you're going to say.
All right, well, thanks. And I'd also like to welcome everyone. I know that getting into Boston at rush hour traffic can be a challenge at times, and so I really appreciate that everyone makes it down here. So with that, I'll just kick right in here. So per Dan's question, I think there's a number of reasons why I chose Michigan Tech. And the first one really comes back to my dad. So my dad was an electronics technician who worked for Willow Run Laboratories that was part of the University of Michigan, later became the Environmental Research Institute of Michigan, and is now actually part of that organization is now Michigan Tech Research Institute, or MITRI, or MTRI, whichever way you want to say it. And so when I was a kid, my dad was this technician. He was also doing work at home. So this is his workbench in the basement. This picture was taken a few months ago, but didn't look a whole lot different with 50 years ago when I was actually down there. And so, but there were, multimeters, there was wire, there was pliers, diagonal cutters, there was soldering irons, and just all these wonderful drawers full of things, just mysterious things to me and stuff. And so I didn't know what they were. But then he also showed me a very important thing about how to make my first electrical circuit. This is a closed loop circuit consisting of a battery, a switch, and a light bulb. And so he taught me how to solder, and so I soldered wires onto each of these devices and made this closed loop circuit. And then when you flip the switch, the light bulb came on, and I was like, oh, this is super cool. And so I was very excited about it, and I took a shoebox, and I put the light bulb out of the shoebox, and I put the switch and the battery and the wires were inside, and I took it to show and tell, and I showed it to all my classmates, and just I took off the lid, and it was very exciting. So very early, and so I think that was my first technical presentation, actually. And so, but that also was this, from that time on, I really, almost my whole life, from that time on, I kind of wanted to be an electrical engineer and kind of going in that direction. And so the other thing I want to use this slide for is also to make, we're going to be talking a lot about bits and some about qubits tonight. And so this is kind of the first exposure to bits as well too, because you can think about when this light is off, you can think of that as a logic 0, and when the light is on, you could be a 1. So we'll come back to that later, but this is my first circuit and my first exposure to bits. So reason number 2 why I went to Michigan Tech is when I was in middle school, my favorite state was Alaska. I loved Alaska. I read about Alaska. I read about people taking dog sleds across Alaska. I read about the geography and the animals and everything, and I really loved Alaska. And so when I started thinking about where would I want to go to be an electrical engineer, I looked at Ann Arbor. Ann Arbor was at the time was 3 times as expensive as Michigan Tech, and also it was kind of close. I grew up in Livonia, which was about 20 miles away, so I kind of wanted to get a little away from home. And so Michigan Tech was as close as I could get to Alaska and still pay in-state tuition. So for those main reasons, I went up to Tech. And so, there were times when, I'm sure that I was dressed like this person right here, trudging around campus. It kind of looks like Tech in the winter time. But there was at least one time when I didn't go outside as prepared for this. And so here's a picture of me in 1984 on the hill between Wadsworth Hall and what was called then Coed Hall, now called McNair. And I'm wearing what appeared to be some very 1980s short shorts with a cutoff t-shirt. I think this was some kind of dare for me to go outside and stand on the remains of our winter carnival snow sculpture that we had put together right out there and stuff. So I'm not exactly sure why I did that, but I think that was the only time when I went out in that kind of clothing. So those are the 2 reasons why I chose Michigan Tech. And so I'm going to go back to my dad here a little bit. So he worked for Willow Run Labs and then IRM. And one of the things that he did was he built a lot of hardware. So he built printed circuit boards, he built chassis, he built wiring harnesses, and he installed them on aircraft because what Willow Run Labs and IRM did is they did a lot of remote sensing. So they would fly airborne test beds, doing synthetic aperture radar mapping or infrared mapping, and so he put these systems together, and then he flew missions on these airborne platforms. And so this is a little foreshadowing, so I'll come back to this later on in the talk. So based on my dad getting me started and wanting to go to Alaska, I went up to Michigan Tech, and when I started up there, I started learning about microprocessors and electronics. There was no computer engineering degree at the time, so it was within electrical engineering, but there was a computer focus, and that's the one that I was in. So I started learning about bits. And so before I move on, how many electrical engineers do we have in the audience here? A few that aren't. And so how many people working with computers and bits and stuff like that? A couple, all right. And so I figured I guess I'm gonna pause it. Okay, here we go. So I'm going to talk a little bit about bits. So this is going to be my bits 101 slide right here. So really, as I mentioned earlier, you can kind of think of like bits as, the on state being a 1, the off state being a 0, and so you can think of a light switch. But then if we're going to try and do this and try and scale it, we need some kind of electrical circuit. And so here I'm showing a complementary metal oxide semiconductor, or CMOS logic gate. And so it consists of a PMOS transistor, an NMOS transistor, a high voltage and a low voltage. And so the way this works is if you put the low voltage on the input, you get a high voltage at the output, so you go from a 0 to a 1. And if you put a high voltage, it goes from a 1 to a 0. So it inverts the state, the logic state of that bit converts from a 1 to a 0. And so, then we can start putting together multiple bits into arrays here that we call bytes. So you put 8 bits into a byte. And then in that you use a binary representation. So you have the ones place, 2, 4, 8, 16, and so on. And so you can create numbers. Here's a 38. Here's 71, and then you can combine a number of different logic gate and ors and XOR gates to create an adder. And so by doing that, you can generate the number 109. So now we can scale this way up to get to our modern computers that have multiple CPUs running at gigahertz speeds with RAM and ROM memory inside and a bus connecting these circuits together. And so we've gone from these very simple logic gates to these things having millions and billions of these logic gates. And then also all the peripherals you connect that to it. So you can have internet routers, you can have computer mice, cameras, microphones, then you've got displays, speakers, and printers, all being connected with bits. So all that information is moving around with bits, right? And then before I leave this slide, one other thing I want to mention, because it'll come back later, is we live in an analog world. So my voice is coming out of here analog. It's going back to that to a microphone on that recorder on that iPad back there, and it's being digitized. And the way we're doing is there's 2 parts to analog to digital conversion. There's a sampling, so we're sampling the signal at the precise instance in time, and then we're also quantizing, so we're taking that sampled signal and turning it into an array of bits that we can then put on the internet, and put onto a DVD. And so for signals when the signal is small, you might have all zeros. When it's big, you'll have all ones, and then for points in between, you have different combinations. So this is my bits 101, and so that's what just wanted to kind of set the stage here, because we'll be talking more about this going on. Okay, and so my first experience with bits, when I showed up at Michigan Tech in the fall of 1982, I took a Fortran programming class, and I programmed on a Sperry Univac 1100. I didn't know this until a couple of months ago when I started putting this talk together. But right then, the processor speed was 7.7 megahertz and about 2 megabytes of memory. Okay, so this is a quiz. Who knows what this is? Anybody? Anybody? Yes? Yes, sure.
Punch card?
Computer punch card, right. So this is the way that I programmed this. So there was these punch card machines. You basically, each punch card was a line of code. And so you typed on this thing and it put little holes in there. And then you do the next line, you do the next line. And you stacked them all together, you ran them through an optical reader, and then it ran through the computer, and at the end you get a printout of that. So that's the way we programmed in 1982, at least on this system. And so there was no backspace key, so as soon as you made a mistake, they had to take it out and you had to start over again. So it was kind of a pain. A couple years later, I took a programming class in Pascal, and by now we moved over to a DEC-VAX system. And here we had terminals, so that was an improvement, so there was a backspace key, which was pretty nice. And then I also, before I go do that, and I also had an Intel 8085 microprocessors. So we were using this to program an assembly language, and so I would program at a lower level in the computers. And so this processor here had a speed of 6.1 megahertz and about 88 kilobytes of memory. So this is sort of circa 1982 to 1985, say. Okay, so now I've been at Michigan Tech for 4 years. I learned a little bit about computing. I learned some about electronics, analog and digital electronics, but I wanted to learn more. And so I decided to go off and get my master's degree, and I had a friend who referred me to Purdue University. So I went down there and I learned about solid state theory. So how materials like semiconductors and insulators and metals work, so I can understand the physics of the devices, and then also how to build larger scale devices, so very large scale integration, design classes, doing layout of transistors in these type of systems. And then I took 2 important electives that changed my life and is really basically why I'm here. So the first one was an introduction to lasers class, and the second one was a radar engineering class. And those will come back later on in the talk here. And then a third event happened when I was there. I actually met Amy, who was sitting right here. And so we met about a month or so after I arrived down at Purdue, and we dated the whole time we were there. And so then we both graduated in the spring of 1988. And Amy grew up in Westford, Massachusetts, not far from here, a little bit west of here. And she wanted to come back to Massachusetts. And I also got a job from Lincoln Laboratory, and so it was a twofer. I was able to come back here and also come back here with Amy, who I then married about a year later after that. And so we just celebrated our 35th wedding anniversary in September. And so now I'm going to give a little bit about Lincoln Laboratory for those of you who aren't familiar with it. So Lincoln Laboratory is a laboratory at MIT. It's a very large laboratory, about 4,600 people. This year we did about $1.4 billion in revenue. It's located out on Hanscom Air Force Base, so about roughly 15 miles or so from the main campus. It was founded in 1951 and primarily does variety of work for the government, applied research and development, both unclassified and classified research, as opposed to the campus, which is more focused on education and basic research. So the tagline of MIT Lincoln Laboratory is technology in support of national security, and that can have a wide range. So there could be defense applications, there could be things like improving air traffic safety, there could be economic security, a whole wide range of things. And what we do is we do several things. We do system analysis and prototyping, so understanding the problems that the nation is facing. We do analyses, and we build prototype systems to kind of demonstrate that. And so if we don't have the components we need, we actually do R&D of advanced electronics and photonics components, work those into the systems, and then demonstrate those. And in the end, we don't manufacture anything, so we do a prototype, and then we do a tech transfer to industry. I'm showing down here the current mission areas of the laboratory. Some of them have been around for a long time, like the Missile Defense Technology area, on which the lab was founded. Other ones are more recent, like there was no Homeland Protection mission before September 11th. And as concerns about cybersecurity arrays, we've added a division here, and our newest one is biotechnology. And so when I first joined the laboratory, I joined the Missile Defense Technology group, and the first program that I worked on was called the Airborne Seeker Testbed Program. So this was an airborne testbed, and the main purpose of it was to emulate a foreign missile seeker. And so what we did is we took it to Stowe Falcon 20 jet, we put a large X-band monopulse antenna up in the nose, we had some receivers, data recording equipment, a forward-looking infrared or FLIR sensor, and then also a C-band beacon tracking radar. And to be able to control this whole system, we had an aircraft computer and an operator control panel, and in that system we had a number of Motorola 68020 computer boards, and so these boards had a processor speed of about 20 megahertz and a memory of 1 megabyte. And so this board right here was about as powerful as that Sperry 1100 whole room computer that was about 20 years earlier. So there's been a lot of advances in terms of getting that computing power. And so when I joined I joined the team, and I knew a lot about electronics and computing, so I helped put the system together, but I also knew a little bit about radar system engineering, so I started becoming a radar system engineer. And on this aircraft, we had 2 pilots, and we had 3 operator seats in the back, and so when my boss came up and said, who wants to go up on the first flight of the test bed, I raised my hand, and so I got to fly on the first mission of the test bed along with my boss and another colleague. And so then what we did is the early flights, we flew right here in the Boston area. So we took off from Hanscom Air Force Base, we flew up over New Hampshire, and we were kind of shaking out the aircraft to make sure everything was working, the systems were all working properly. And then promptly after that, we went off to Holloman Air Force Base outside of Alamogordo, New Mexico, and we flew missions over the White Sands Missile Range out there. And then over the next 3 years, I flew about 150 missions on the test bed all over America. I flew over the water, I flew over the deserts, I flew up in northern New York in the wintertime, and just had this really very interesting first job out of school, putting a system together like that and flying on board this airborne test bed. And one really interesting event happened toward the end of this, it was in 1993. Remember my father, who I told you flew around in planes and did field tests? we discovered that we were both in California, both out doing field work at the same time. And so we got together for dinner in Ridgecrest, California in 1993, and I bought him dinner. And this was one of the favorite stories that you like to tell, how my son, you know, now we met up in the field, and now my son bought me dinner. So it was a really great moment, and it was kind of like a father like son moment. Okay, so now I'm this radar system engineer, electronics, bits guy, and so like, how did I get to photonics and qubits? Well, we had a requirement that we needed to get data from a wing pod into the computer in the cabin. So we thought about how are we going to bring that data in there into the cabin. And so what we decided to do is use a digital fiber optic communication link. So this was the early 1990s, and these links were just starting to become deployed. And so the way that works is you have some data source. This is my sensor out in the wing pod, and I'm creating my ones and zeros, my bits, streams of bits. And I go through a laser driver that hits a directly modulated laser, converts those bits into on-off pulses of light, kind of going back to that on-off of the light switch I told you about. And then we detect them on the other side with a photodetector, and then receive them. And now on this side, I've got the ones and zeros coming through in my sync, going into my aircraft computer. And so you may remember, Paul also took a course on Introduction to Lasers, and so I was like, I know about lasers a little bit. And so I started speccing the system out. We ran fiber optic cables through the wing of the aircraft, and I was like, oh, this is really cool. This is what I want to do. And I started poking around Lincoln Laboratory a little bit, saying, you know, asking other groups, can I join your group? And they're like, you don't know anything about optics or photonics. And like, this is true. And so finally, Amy suggested, another great suggestion she made, is that I should go, maybe I should go back and get my PhD. So I decided to do that, and after a lot of discussion and looking around different places, I decided to go to Georgia Tech down in Atlanta. And down there, I learned more about optical communications, and this is actually a transparent optical packet switch that I helped build and characterize. I did ultrafast spectroscopy, so taking very short pulses of light, sub-picosecond pulses of light, hitting materials and then looking at how they responded to those short pulses of light. And I worked in a clean room fabrication facility, learning how to make compound semiconductor devices, and some of those devices that I fabricated were indium gallium arsenide quantum optical modulators. And this is a picture of the characterization setup that I used to test those out. And then after we finished up, I finished up down there, it was 1999, the telecom boom was going on, so I had offers from large companies, startups, but then I had met some people from Lincoln Laboratory who were doing optics and photonics, and they drew me back in. And so I went back to Lincoln and I've been back there ever since. And so, as I mentioned, I was in this air and missile defense technology group before when I first left, but now it was more appropriate for me to move over to the advanced technology mission area, and so that's where I've been this past 25 years. And so, all right, now this is going to be a whirlwind tour of Paul's last 25 years doing photonics at Lincoln Laboratory. So we're going to do this in one slide. So first thing I did for the first 4 years I was there is I worked on photonic analog to digital converters. So when I was talking about it earlier, we're using electronics to sample the signal. Here we use short pulses of light that have better timing resolution than you can get out of electronics. And so we were able to make the best 500 megasample per second ADD converter of any type of form in about 2003 we did that. So that's what I did. I was a technical staff there for those first several years. Then the next thing I did was I developed a new class of semiconductor optical amplifiers. So here, if you want to take an optical signal and boost it up, you go through an optical amplifier. And these SOAs, if they don't have a large enough saturation power, they will clip and you'll distort the signal. And so at the time, the highest output power was about 100 milliwatts, or a tenth of a watt. We developed devices that were put out about 10 times higher than that. It was about a watt. And so we did a lot with these different devices. But the thing I'm almost most proud of, or probably most proud of, is we developed use them for a power amplifier and a gas mapping LiDAR system. So this was a collaboration with a small company called Bridger Photonics. And these are used now for mapping, it's methane, looking for methane emissions. So if you may know, methane is a very potent greenhouse warming gas. And so these Scala devices are now being used to reduce global warming. So I thought that was kind of cool. And here I was a technical staff, and then I became an assistant group leader as well. And for the past 10 years or so, I've been developing photonic integrated circuit, or PIC platforms. And here what we're trying to do is take lasers, modulators, low loss waveguides, and photodiodes, and put them all onto one integrated circuit. Similar to the ways you might make a larger, like a CMOS circuit, but using these different types of materials and different devices. And here we have applications in quantum, microwave photonics, and then lasers and sensing. And so each of these topics here could be an hour-long talk, but that's all you're going to get for today. So I'm happy to answer some questions if people have questions later on. And so while we were developing those PICs for those applications, there was a lot going on in the telecom world here, datacom world. And so because as you increase the power of the computers and you get the internet set up, you had to have data centers for moving data around and storing data. And so here they're using fiber optic cables to be able to transmit and receive data. But then there's always been these drivers for going for more integration. So you have a certain amount of area on this, and so you want to get more gigabits per second per area on the faceplates, decreasing component costs, reducing packaging costs, and going to advanced modulation formats. And so people have been now also been doing this for a number of years now, putting lasers, modulators, photodetectors all on a common chip. You can do that for a number of different techniques, and now there's more than 1,000 devices all on a PIC. And from one PIC to another PIC, you can transmit more than 2 terabits per second. So 2 times 10 to the 12 bits per second from one little photonic integrated circuit. So it's pretty crazy advances that have been made in this area. And the reason we really need that is because how much microprocessors have evolved in this time. We have in this chart here, what I'm showing on this axis. On this axis are a number of different things. So this is transistors in thousands, so you have to multiply this number by 1,000. It shows the frequency in megahertz. It shows the watts of power that are dissipated in these microprocessors, and also the number of logical cores. So over the past 40 years, since I've been starting getting involved in bits, there's more than 1 million times transistors in one of these microprocessors. There's been 1,000 increase in clock speed. And as you can see, the clock speed actually has kind of leveled out here, and that's because of the speed limitations of the CMOS technology. But then also, we also have issues here that the top type of power, the power density you can get in one of these sort of leveled off as well too. And so what people had to do is go to multiple cores, so your multi-core processor to be able to increase the power of these things. And so, as I was putting this talk together, I was like, what's the most powerful chip that's out there right now? And so I did a little digging around on the internet, and this NVIDIA Grace Hopper super chip seems to be that. And it's not just really one chip, there's a lot of chips in here, but what it does is it actually has a processor speed of 3.1 gigahertz. There are 72 CPU cores, so processing unit cores. There are 17,000 GPU cores, according to I thought that kind of blew me away, that there's that many graphic processor units there. Hundreds of gigabytes of memory compared to those kilobytes we had 40 years ago. Chip-to-chip data transmission of 900 gigabits per second. And overall, this whole thing has 200 billion transistors. So it's pretty impressive how far we've come in sort of the 40 years since I was programming that Sperry UNIVAC 1100 in the basement of the ERC. And so that's where that's a long answer, a little bit of introduction mine now. And so what I'm going to turn it over to Dan now and talk a little bit about quantum and some of the volunteering work that I did after that. So.
Great. All right, so the title of the talk tonight was From Bits to Qubits, and so we're still on the bits part, okay? So Paul's described his sort of evolution in the world of bits from being at Michigan Tech, and I'm going to talk about that too, because I want to tell you a little bit about what's happening at Michigan Tech, if you're not familiar with what's happening with computing. Yeah, let me grab it. Yeah, clicker. Thanks. So just very quickly, just a little bit about me. I grew up in northeast Oklahoma, a couple of towns called Bartlesville and Tulsa. Went to Washington University in St. Louis for my undergraduate. My graduate work at Princeton. There's an interesting story about why those two buildings look exactly the same. We can talk about that later. I actually went back to Washington University and was on the faculty there for 24 years in electrical engineering, which became electrical and systems engineering, and went through the whole process there. Around when I was about 50, I had a midlife crisis and decided I wanted to do something a little different, and started looking at department chair position, and was recruited by Tim Schultz to become department chair in the ECE department at Michigan Tech. And then I'll talk in a little bit. I've been at Michigan Tech ever since, but now I'm in a different role. I'm a department chair for a different department called Applied Computing. My technical background is in radar signal processing, so some of the things Paul was talking about, and I'm an IEEE fellow in that area. But I really just want to talk about what's going on with computing at Michigan Tech. We do have a long history. You're probably aware of that in fact, just this past year, we celebrated the 50th anniversary of the undergraduate program in computer science. So, and the computer science department has been, actually came a few years later, but it's been around for a very long time. And there's computing in all corners of Michigan Tech. And there's been a steady evolution of of new programs, and the enrollment's growing. And we added the computer engineering program and electrical engineering around 2000, and just you can't read everything that's on this chart, but there's been a steady growth of computing at Michigan Tech, as you might imagine from all the technology development that Paul was talking about. But more recently, I'd say in the last 10 years or so, a lot of people at Michigan Tech were thinking, what are we doing in computing? Are we doing enough to say that computing is important and that we do it? And so there are some efforts to kind of group things together. There was this thing called the Alliance for Computing, Information, and Automation that started in 2014 that involved a few departments, including my own. And in 2017, the Board of Trustees asked the provost, what's Michigan Tech doing in computing? Because they really didn't know. And so they formed a working group to sort of look at all what we're doing, what other schools are doing. And in the end, at the end of that year, and I was the head of that working group, at the end of that year, we recommended forming a College of Computing at Michigan Tech. And that coincided with the arrival of our current president, Richard Kobach. And after about a half a year, after about a semester, he said, yeah, we're going to do it. We're going to form this College of Computing. And so when that was founded in 2019, we have the CS department came over from the College of Sciences and Arts, and then some programs from the School of Technology in electrical engineering technology, computer networks, health informatics. They came over and they formed what is now my department, which is the Department of Applied Computing. So why do we want to do this? Why do because and there are arguments pro and con about having computing be a separate unit at a university. In many cases, it's either going to be in the engineering school or it's going to be in arts and sciences somewhere. But there is a movement in this direction of creating these colleges of computing, and especially at Michigan Tech, we're a technological university, right? And what's the dominant technology of our time right now? It's computing. In fact, I always show this chart. That's a chart from 2017, but it shows the market cap of the top companies in the U.S. And the top 5 are Apple, Google, Microsoft, Facebook, and Amazon. Okay, so that's where all the action is. And so that was one of the arguments we made. We talked about the demands in industry and society and so forth. And the issue at Michigan Tech was we were doing a lot of computing, but it was hidden because it was everywhere, right? It was all kind of spread out. And we said, if we're going to elevate the stature and the impact on the visibility of computing at Michigan Tech, it needs to have its own. Unit. So we did that, and in so doing, we joined a national movement of other universities. There's not a whole lot, but there's a fair number of universities now that have colleges of computing, including several right here in this area. Northeastern, MIT. MIT started theirs the same year we did. Georgia Tech, Rochester Institute of Technology. We visited some of these places. It was really eye-opening. That picture there, by the way, is the atrium of the Interdisciplinary Science and Engineering Center at Northeastern, if you're familiar with that. It's jaw-dropping, and I took that photo. That was something to see that. So what are we now? Sorry about the org chart here, but basically the point here is we have 2 departments. On the left is the Department of Computer Science. On the right is the Department of Applied Computing. Computer Science has their programs basically in computer science and software engineering. And on our side, we have a number of different things: information technology, EET, mechatronics, health informatics. Basically, the distinction between the two is that the CS department focuses on programming and the mathematical foundations of the field, and my department is more infrastructure. So we're not theoretical. We're not doing software development. We're doing infrastructure for helping software development. So that's in broad strokes. It's been a success. Okay, the college is really taking off. If you look at our enrollment, before and after the development of the college, it's taken off. We're now at 1,200 and some students altogether. And the interesting chart down here at the bottom shows the percentage of students at Michigan Tech who are in the College of Computing, and that's been growing steadily as well. So right now we're a little under 17% of the entire university. We have aspirations to be 25% someday soon. We'll see. And the research is doing really well too. We have an institute at Michigan Tech, which is not just in the College of Computing. It's actually campus-wide, but it's called the Institute of Computing and Cyber Systems. It has a lot of people from College of Computing, but other units as well. And it's going great guns as well. Lots of new awards, and so we sort of look at award amounts per year, but also research expenditures per year, and everything's going up and to the right. So we like to see that. And so, what does the future hold? Where are we headed? Of course, we're talking about artificial intelligence. Everyone's talking about artificial intelligence these days. So we do have a lot going on all across the college in that area. Data science is big. We're most likely going to have a new department in data science within the next 3 years. That'll take health informatics. We do a lot in cybersecurity. We're developing those programs. That's shared by the 2 departments, but we're looking to see if that might be its own department someday. We have programs in mechatronics with the College of Engineering, and so we're trying to figure out how to balance all that. And we are just getting started with quantum computing. We have a couple of courses. It does turn out that quantum computing research is expensive, and so we're not really developing any facilities for doing quantum computing hardware research. But who knows what the future holds. I brought copies of this, by the way. This is our Gateway magazine from the College of Computing, and it's around here somewhere, and I'll put those out for you if you want to take a look before you leave. But anyway, that's the story of what's happening with computing in Michigan Tech right now. And I think with that, as sort of an intermission, I turn it back over to Paul, because now we're going to go from bits to qubits.
Thanks, Dan. So, how many quantum physicists in the audience? Yeah, me either. So like I said, as I've been telling you, I'm an electrical engineer. I happen to be leading a group that has a lot of quantum physics in it, so I've kind of learned along the way here. What I'm going to be trying to do, give you a high-level overview of quantum computing, and so I understand it a little deeper than this, but not a whole lot deeper than what I'm going to be talking about today. So if you look at quantum information science and technology, there's really 3 primary areas. There's quantum computing, which is developing the technology to solve problems that are intractable by classical computers, and I'll talk a little bit about what some of those problems are. There's quantum communications and networking, how we can take quantum information and move them from one place to another, perhaps over optical fibers. And then also quantum sensing, which allows alternative sensing modalities to overcome classical limitations, perhaps in sensitivity, stability, and size. And so Lincoln has activities in all 3 of these areas. The group that I lead does both quantum computing and quantum sensing, and I'll just be focusing on the quantum computing in this talk. All right, so I talked about what a bit is. Let's talk a little bit what a qubit is. So in what we were talking about is these bits. So classical bits, the 1s and 0s, the on-offs, the CMOS logic gate. We can also think about classical mixtures. So say I have a number of red balls and blue balls, and I put them into a bag, and I start pulling them out. I'm going to get, if I say I have 7 of red, 7 blue, I'm going to pull out 7 red and 7 blue. They're just very defined. They're not going to change at all when I'm putting them in the bag and pull them out. If we now look at the quantum side of things, first of all, I still have 2-level systems, 0 and 1, but now the bits can be both 0 and 1 at the same time. There's some probability they're going to be in a 0, there's some probability that they're going to be in a 1, and they also can have a phase relationship to them as well, so that they basically exist anywhere on, this is what's called a block sphere, and so this qubit can have a representation anywhere on the surface of this sphere. And now when I look at putting qubits into a quantum superposition state, I put them into the bag, and now they're neither red nor blue, but they're somewhere in between. They can be both at the same time. And it's not until I actually measure them that I knew what the quantum state is. And so once I've done the measurement, then the wave function collapses, and I can determine whether they're a red ball, a red bit, or a blue bit. And so there's some metrics here that we care about. The coherence time. When we have like a digital circuit, if you put it in a 1 state, it'll stay in a 1 state for a long time. Here with quantum bits, they can toggle between the 2, and so how long does the qubit hold on to that quantum information? It gets disturbed by noise. How quickly can a gate operation be performed? So we have like this gate here, this CMOS gate. There's comparable gates in the quantum world. How quickly can you perform that operation? And then how accurately can the gate perform it? If you do it 100 times, how many times does it do the right thing? So those are the key metrics that we're looking at. There's a wide range of technologies that people are looking at to make qubits, ranging from things like neutral atoms or ionized atoms or ions that actually hold these 0 and 1 states. You could also think about using photons and maybe using the polarization, like a horizontal polarization would be 1 state, a vertical polarization would be another state. And then you can also design qubits, more manufacturable qubits. So there's superconducting qubits where you have electrons trapped in 2-dimensional gases, or superconducting qubits where we actually can build a nonlinear resonance circuit, cool it down to about 10 millikelvin above absolute zero, and then actually perform quantum experiments and quantum operations down at that temperature. And right now, to be honest, no one knows what's going to win. People have their bets and stuff like that. There's a lot of money going into different, IBM and Google are putting a lot of money into superconducting qubits. Other companies like IonQ are looking more at this trapped ion approach. At Lincoln Laboratory, we're looking at both trapped ions and superconducting qubits. All right, so this is my one slide on quantum computation. And so at a very high level, what quantum computation is any algorithm that leverages the quantum superpositions that I described earlier or quantum entanglement. And so I'm not going to go into what quantum entanglement is. I do have a backup slide if people want to see that slide. But as we talked about with the classical computer, we have these bits. And so if I have 3 bits, I can represent one 3-bit state, and the numbers I can represent are between 0 and 7. If I now have 3 quantum bits, each of these has a probability associated with it, what's going to be. So now instead of having just one number, I can now have a total of 2 to the n components to that one state. And so with 3 bits, I can represent 8 different components to that state. And this scales really rapidly, as you might imagine. If I have 256 qubits, that's 2 to the 256th, or which is about 10 to the 77th, which is also the total numbers of atoms in the universe is about 10 to the 80. And so you can get very big numbers very quickly. And so if you're looking at classical computing, when you're trying to do parallel processing, you take a different processor that's operating on a different number, so you can put 000 through here and get the function of the operation on that, same as 1. But when you're doing this quantum computation, what you can do is initialize this big state of qubits, put it through your quantum computer, and it operates on that whole state at once. And so it can really potentially greatly accelerate the rate that you can do these computations. So that's what I'm going to really say about quantum computation. There's a number of different applications and classes of quantum computers. One is a quantum annealer, and the idea here is this potentially could be used for solving optimization problems, like the traveling salesman problem about finding the shortest path for going out and doing the sales. And here, to date, there really hasn't been theoretically proven that you can get quantum speedup. The typical size here is more than sort of 1,000 what we call annealing qubits. So you sort of initialize all these qubits to a certain state, you let them settle to their lowest energy state, and then you read it out. They are commercially available, so there's a company called D-Wave that you could buy this from, but it's really, to my knowledge, it's really never shown any quantum advantage from those type of systems. Where we are right now in terms of gate-based quantum computing is we're in an era called noisy intermediate scale quantum computing. And here, the potential is that we might be able to do things like quantum chemistry or drug development, material science. So there is potential for quantum speed up here. And we're kind of like, we have systems this kind of size, sort of 20 to 1,000 qubits. You can actually go on to Amazon Web Services right now and program and run programs on a quantum computer. IBM has something similar to that as well too. But most of the problems they can solve at this point are more toy problems, and they're not really providing significant quantum advantage. And then where we're trying to go is something called universal fault-tolerant quantum computing. And here the main driver for that that's gotten people all excited, especially within the government, is that if you could build such a computer, you could break RSA encryption codes pretty easily. So if you have like a 4096-bit key, if you were going to use the best supercomputer out there, it would take more than the age of the universe to break that code. However, if you had the appropriate quantum computer, it would take about an hour. And so, as you imagine, that given people places like the NSA have a lot of concerns about things like that, right? So, and what you can do, you could do other things like factorization, database searching, linear equalization sampling. And so it's definitely for some select applications, this is theoretically proven to have speed up, but you need sort of 1 million qubits. And right now we're sort of at tens to 1,000 qubits. So we're still a ways away. And so while we may have this, we're probably still looking at least 10 years till we get to this. There's a lot of investment, there's a lot of companies, startups out there, and stuff like that, but we're still in this regime of NIST computing, and we're still working toward these larger scale computers. Okay, so just briefly talking about my personal journey. So I started at this Sperry Univac back in the basement of EERC back in 1982, and recently I had an opportunity to go visit sort of one of what I consider the state-of-the-art systems. This is at IBM's Thomas Watson Research Center in Yorktown Heights. And so they have IBM System 1 and System 2, and these were, you may have seen this on 60 Minutes in the past year, so they had a special on that. And I was there partially as my role as leading this quantum information group, and I got to meet with some of the quantum physicists and see these systems there. So I thought that was pretty cool to go from this unit back to this. But if I want to solve problems, practical engineering problems today, you know, I have to admit that I probably use the spare UNIVAC rather than this, because they're still not, you know, the kind of problems you solve are really more toy problems at this point. There's a lot of great advances here, but they're still working out the right algorithms, the error correction, everything to really make these useful. But it's a stepping stone. And so the group that I lead at Lincoln is called Quantum Information and Integrated Nanosystems. It's been around for 10 years now, and you can blame me for the long name. I was partially responsible for coming up with the name for that group. But really our mission is to expand the frontiers of computing and sensing using both quantum and classical techniques. We do that around a variety of technology platforms. We have a superconducting platform where we're doing superconducting qubits for quantum computing. We also do classical electronics, high-speed electronics, and also detectors and interfaces. We have a trapped ion platform, both for quantum computing and also to develop improved optical atomic clocks to make maybe better GPS systems or better timing for other applications. And then we also have a solid state platform where we have, mostly here we're doing nitrogen defects in diamond and using that to precisely measure magnetic fields for doing things like magnetic navigation and imaging of magnetic fields as well. And then we have an integrated photonics platform, and that's part of the group that I have the most familiarity with, because I help bring this part of the group up. And we have ways that we're feeding into these other platforms. We have a number of core competencies in the group, ranging from theory simulation, design and layout, to materials growth, fabrication and processing, integration and packaging, and testing and data analysis. So all of these within our group to be able to feed into these platforms. And then we work with folks outside of the group to do quantum networking with the technology. And then also on the classical side, we're developing integrated photonics for microwave systems and for lasers and sensing. So here's a picture of the group. This is actually about 2/3 of the group. This was taken last January. We're about 150 people right now. And so this was, we did this after a luncheon, post-holiday luncheon. And so it's, you know, I've been leading the group for about the past 3 years, and it's been a real honor to get to work with these scientists and engineers to kind of be pushing all these technologies forward. Okay, so now that's all the technical part. And now I've also had a lot of opportunities in my career to do volunteering, and so I'm now going to talk a little bit about some of my volunteering experience, particularly I'll touch upon the work that I did with Michigan Tech as well. So I want to start with a couple of, you ever have those kind of moments when you're just like, how did I get here kind of a moment, stuff like that, you know, so how, you know, I don't belong here, so how did I get here? Well, first I'm going to start by saying, who remembers that 2015 was the UN designated International Year of Light? Andrew remembers. Well, I probably wouldn't have known that if I hadn't been at the time the Vice President of Membership for the IEEE Photonics Society. And as part of that role, I got to attend the opening ceremony of the International Year of Light at the UNESCO headquarters in Paris, France, which was pretty cool. And so there's a picture of me listening to a translation of a speaker who's speaking in Arabic. And so it's like at the UN, you got the headphones on and you're hearing what the person's actually saying. And so my wife, Amy, actually took the picture. She came along with me for this. We actually, at the time, were celebrating our 25th wedding anniversary, and so Amy saw some of the opening ceremony. She didn't stay for all of it because she decided to run around Paris a little bit, and so then we also got some opportunities to do that. Here we are down by the Seine. So that was one. The other one, you know, when I was an undergrad electrical engineer working in the basement of the MIRC or studying the library or working in some of the labs, I never in a million years thought I'd be inducted into the electrical engineering department's ECE Academy. But you know, from my involvement with the department for 16 years serving on the external advisory committee, and then also you know, through my technical accomplishments, I got inducted in 2018. And so some of you may know, I was inducted the same year that Doc Wheaton got inducted as well too, which was kind of a great honor to be inducted with him. And so once again, Amy came along to that venture too. And so after the event, we spent some time down on the National Lake Shore down at Picture Rocks, and there's a picture of us down by Chapel Rock. And so I'm going to talk a little bit about how I got started in volunteering. I've got quotes around volunteering, because you can decide for yourself whether you consider this to be volunteering or not. But when I was at Michigan Tech, I helped found a student organization for people who didn't necessarily want to join a fraternity or sorority. And so it was called IPICs. And these are some of the main people who live in the IPICs house. And so it started off as something small and grew. And we had, at one time, we probably had about 100 people on campus involved in this. And we'd have big parties. And at the end of every party, it was kind of a tradition that everyone in the whole party would have their arms around each other, and we'd play Billy Joel's Piano Man, and we'd be swaying back and forth the Piano Man. So, but you can see some trophies in here, and so we did participate in homecoming, and to be able to participate in homecoming, you have to be a registered organization. So my colleagues, my friends said, well, if we're gonna do this, you can be the president, because if we get in trouble for this, you're gonna go down, not us, and stuff. And so I was the president. I came up with an Articles of the Constitution, and we were approved by the Dean of Students to be on there. And so here's a picture of me participating in the root beer chugging relay race at homecoming in 1984, and I'm wearing the traditional hobo garb that is no longer, I believe, has been kind of phased out since that time. But back then we kind of dressed like that during homecoming. So that was that really volunteering? I don't know. I was president, but it was also just a lot of fun with my friends and colleagues as well too. So I'll get into a little bit more on the next slide. But since that time, I have done a lot of volunteering, and I really think of a person's life being broken into 3 different parts. I think of your personal life, your time with your wife and your family, your kids, having fun, going to your hobbies and stuff like that, your personal life. Then there's your work life, what you're doing in your career, paying the bills and things like that. But then there's also this third wedge called what I call a volunteer life. And not everyone does volunteering, and I think you can have a great life but not doing, just having a personal and work life as well too. But the volunteering gives you some different aspects to your life I'll talk about later. But really, I think the first formal volunteering that I did was when I was at Georgia Tech. I was the organizer for a graduate seminar series where we brought together people within this Microelectronics Research Center to bring together faculty and students to talk about the different groups and give the grad students an opportunity to give talks. And so I helped identify the speakers, I reserved the rooms, I got the food all going and stuff like that. And so I really I ran that for about a year there. And this was my first real formal step into volunteering. And then after I came back to Lincoln Laboratory, I've been heavily involved in volunteering ever since. I won't go into all the details here, but this is my 20+ years of volunteering. Doing volunteering activities for Lincoln Laboratory, down with people on the MIT campus, and then getting involved in the IEEE Photonic Society, which was formerly the Laser and Electro-Optics Society, getting involved there. And then also a big conference for our area called the Conference on Lasers and Electro-Optics. And I do just want to highlight here my involvement with Michigan Tech. When I came out, I started recruiting for Lincoln Laboratory, and soon after met Tim Schultz. And Tim invited me to serve on the External Advisory Committee, sort of in about 2000. And at that time, they were trying to grow the graduate program. And here was someone from Michigan Tech, but also had been gone off and gotten a PhD and was involved in research. And so they liked that. And I also knew about photonics, and Tim was also just growing the photonics program, and I helped with that as well too. And then I met Dan in 2008 when he joined the faculty, and got to work with him for another 8 years while I was serving. And I don't know if you want to mention anything about the EAC, Dan, or no? Okay, but the EAC is sort of a board. There's some official purpose to it for getting accreditation to make sure that but it's also really kind of just an opportunity to meet with faculty and help provide some guidance to the department. So, and just in a variety of areas. And so, that's that was my Michigan Tech involvement in volunteering. And then there's been a number of other people along the way that have helped me out. Katie Hall got me involved with a subcommittee for the Laser and Electro-Optics Laser and Electro Society annual meeting. Joe Donnelly from Lincoln Lab got me involved in the Conference on Laser and Electro-Optics, and through that initial invitation, I became subcommittee chair and program chair and then general chair of a 4,500 person meeting. And then Jim Coleman invited me to run for the Board of Governors for the Photonic Society, and I served on the board. And then also Domino that got me involved in to be vice president of membership on that society. So a number of people who helped me along my way in my volunteering career. And last, but definitely not least, my son James, who when James was 6 years old, he's a little older than 6 here, but I decided he wanted to play soccer. We signed him up for soccer, and I decided that I wanted to be a coach. But growing up in the Midwest, I knew nothing about soccer, and so however the head coach did, and so I was learning as the kids were learning. I learned how to strike a ball properly and everything, and then but over the past 20 years, 15 years, 56 years, soccer has become a huge passion for me. It's my favorite sport. It's the only really sport I really track. And actually, my wife and I, we're going to Liverpool in a couple of weeks to go see Liverpool play Brighton and Hove Albion at Anfield. And so, if it wasn't for this kid and getting me involved in volunteering, I would have never had that either. So that's my volunteering story. And to sort of summarize it up, I had an opportunity to write a little article about this, and I came up, here's this what I call a volunteer life model. And so if you're going to volunteer, it's going to take time. It's going to take time out of your work. It's going to take time out of your personal life. It takes time. And you also donate other things too. From your work life, you might bring your skills and your work network, and from your personal life, your experience and your family and friends. So things are going into your volunteering life. And then, however, the volunteer life also gives back as well too. And from on the work side, when I was vice president of membership, I did a strategic plan that I was able to bring back and the knowledge I gained there for doing that, strategic thinking, leadership skills, career opportunities, expanding network, and professional recognition. So I'm a fellow of both the IEEE and a society called Optica. And while you can primarily do that for your technical contributions, I don't believe that I probably would have been done doing it. I would probably not receive that recognition, and I also help an active volunteer as well too. And then on the personal side, you get this unique experience, friends, travel to Paris with your wife, all sorts of things like that, and also this personal satisfaction that you've given back to something and try to make something a little bit better as well too. So I really like this model, and it kind of really shows how you're putting things into your volunteer life, but you're getting things back as well. Okay, so I'm just going to wrap up the talk right now with some acknowledgments. First, I'd like to acknowledge Professor Anand Kulkarni, who was my favorite professor at Michigan Tech. He taught a lot of the electronics classes, and I learned a lot from him. I believe he's a professor emeritus now, is that correct?
Quite a while, actually.
Yeah, okay, yeah. And so Anand, Professor Kulkarni was a great person. And then Lincoln Laboratory, who gave me that first opportunity to go to work and fly around in that aircraft and get me thinking about things beyond just the master's degree and wanting to go back and pursue a PhD. And then they've also supported me along the way, both technically and also allowing me to volunteer, all that volunteering things that I've done. So that was great. So I thank all the people and all the people at Lincoln Laboratory as well. And then the last thing, I'd also like to thank my family. So, sorry. So my father, who got me started, I knew this was the part I was going to break down. So he passed away a week ago Wednesday, and so I was planning to show him these slides, but I never got a chance to do so. He's the one who got me started. Here's a picture of us out at one of the old Willow Run hangars, building 2080, where he worked a lot of his career. This was about 3 or 4 years ago. We went back there, we drove around, and so I got a picture of him doing this thing. And I'd also like to thank my family, James and Amy. Amy's really been there supporting me the whole time, and I really thank her for bringing me out east, and then also allowing me to go off to Georgia Tech and get my PhD, and just kind of being there while I'm doing all these kind of crazy things and stuff like that. So thanks a lot. I appreciate your attention, and happy to take questions.
So I guess I'm the moderator for the questions. Is that right, Jen?
Yeah.
Okay. And if people have questions, should I bring the microphone to them?
Sure. Yeah. Unless
it might help for the recording.
Or project. Yeah.
So, Paul, first of all, thank you very much. And it kind of reminds me about sort of our lives are all sort of non-linear, right? I mean, we don't always move in the same direction. And it's like breathing in and breathing out, right? You develop one relationship, and then you find out years later that it comes back the other way, and then and things kind of go around in a circle. And I think that's absolutely true with Paul. It's been a real pleasure to get to know you over these past 16 years and sort of see where you came from and where you came back and all the volunteering you're doing. And so I think that's a good lesson for all of us, the kind of life that you've led here. But let me open it up to questions, and if you have questions for Paul about anything, or me for that matter, if you want to talk about computing at Michigan Tech, which seems kind of small in comparison to that Paul talked about, but very important. Yeah.
Professor, what was that term, mechatronics?
Mechatronics?
What is that?
Mechatronics is it's a term that means a field which combines electrical systems, mechanical systems, and computing. So you can kind of think of it as synonymous with robotics, because robots have the same three things, right? They got mechanical parts, they got electrical parts, they got computer parts. Mechatronics is a little bit larger. Sometimes People use the word mechatronics when they're talking about industrial systems a lot of times, and robots, you think about robots, right? And so you can have systems that don't look like robots that are still completely automated, like an entire factory or those sorts of things. And so we actually have both programs in Michigan Tech. In ECE, there's a robotics engineering program now, and in my department, we have a mechatronics program. There's a lot of overlap between the two. But you can, the quick and simple answer, which I obviously did not give, is that it's like robots. Yeah.
Okay. I have like 3 questions. First one, so the IBMs and the Googles must be trying to poach from your group. Is that right? Or is it just like theory versus application? You're like, they have no interest?
That's not true. So yeah, so there's, yes. And so one of the interesting things about Lincoln, it's a great place to work, although we can't quite pay what the people in industry can pay and stuff like that. So there's definitely interest from there, and some of our staff members have gotten offers considerably higher than what we can pay. We have certain pay scales that we can pay them. And so, however, we were able to partially meet some of those, and then also just work out ways to be able to retain people. But it depends on what you really want to do. I mean, they're still doing kind of some interesting research, so they're doing great work there and stuff too. Our focus is a little bit different. We're not trying to build a universal fault tolerant, large scale, million Bitcoin. So we're trying to understand some of the basic building blocks and think about things like how you scale to larger numbers, and how you interface to those qubits, and what happens with crosstalk and trying to get coherence up. And so there's a lot of, and actually we came up with a way for doing 3D stats to be able to get the qubits away from the readout layers, and actually IBM is using that same approach. So there's things we're doing that's sort of feeding into what's going on in industry. But you're right, our people are in high demand, and it's hard for us to actually be able to even hire people in, because they can get a lot more if they want to go to Google. So.
Yeah, I mean, I can see the research appeal for sure, and that makes a lot of sense. But like, man, you must be facing kind of a beast there.
It is.
My second question is also a little bit selfish. Sorry, everybody. You mentioned that you worked to like reduce methane emissions.
Yes.
Can you tell me more about that?
Sure, yeah. So I mean, I just kind of, it was a lot. I covered 25 years in a pretty short period of time. So,
yeah.
But yeah, the way that so this company called Bridger Photonics, what they do is they make a system, a LiDAR system, laser, it's kind of laser radar kind of system that is able to. What they do is there's a methane absorption line at 1.65 microns, a wavelength of 1.65 microns, and what they do is they take a laser and they sweep it back and forth across that absorption line, and then they can demodulate that, and they can tell. Basically what they're doing is they're shining light down, this 1.65 micron light, they're shining it down, it's bouncing back up, and if there's methane in the way, they can detect that methane. And so one of the issues that they had was that wavelength, there's not a really good way to amplify the optical light, and so to be able to transmit a long distance and come back, you need to have a certain amount of optical power. So we built these higher power optical amplifiers that allowed them to increase their range by about a factor of 3 in terms of being able to do that. And so what they do is they just fly over, and then what they're just doing is, say, flying over, and they're just keeping track of where they're looking with their system, and then they just build maps of methane. So they fly over, say, like gas fields or gas pipes and stuff, and they can see plumes of methane coming off, and it's real. And so there's a lot of people interested from the Environmental Protection Agency, but then also from companies as well too, because at the end, companies don't want to have methane spewing out of pipes. It's because there's a loss of profit as well too. So. Do you have one more?
I do, but it's completely unrelated. So
Okay,
here's a follow-up.
I had a question between Draper Lab and MIT and Lincoln Lab. What is Draper?
Yeah, so the difference between Draper and Lincoln Laboratory?
Yeah.
So Draper was also at one point a laboratory of MIT as well too. And so they really focused a lot on inertial navigation systems. That was their big bread and butter and stuff. And so what happened is in the early 1970s, when there was a lot of student unrest. I mentioned earlier that Willow Run Laboratories at the University of Michigan became IRM. That also was the same thing that the students kind of pushed, and they diversified from that defense research that was going on. And so Draper Lab was down on campus, And so that was much closer. Lincoln Laboratory was 15 miles away out of Hansen Air Force Base, and so there wasn't as much. And so we were still part of MIT. So I'm an MIT employee, but Draper, sort of divested from MIT.
I used to work there.
Okay. Am I correct? Was that my story correct there, pretty much? I think early 70s.
They got kicked off too.
I did some nozzles for navigation of material drive.
Okay. Right. Other questions? Yeah, sorry, right there.
Yeah. So you saw the advancement during your career from computers the size of small rooms to something a million times more powerful in our pocket. How do you think the scaling of quantum computing will compare to that? Do you think it has unique challenges that will really hold it back due to the nature of it? Or will we see similar advancements over the next 10, 20, 30 years?
That's a really good question. I think one of the things that struck me a while ago when and I think other people had the same thought, one of the interesting things about classical computing was as soon as you built a computer, even a simple computer, you could use that computer to design the next computer. And so there was a cycle there to be able to do that. With quantum computing, at least right now, you're not able to use those simple computers, the simple quantum, to do anything to design the next kind of. You're kind of learning some things and stuff like that, but I think that there's a different in the way that they're going to advance. And then also too, like the reason why we've got scaling is because there's sort of the Moore's law scaling that a lot of processes, and it's going to be different scaling laws for quantum computing. And so, but that said, especially like a lot of these things do have to be cryogenically cooled, and so I don't think we're going to have a quantum computer on our wrist any time in the foreseeable future. So, do you have a third question back there?
So you said just under 17% at Tech, the applied computing?
That's right.
That's amazing for like a relatively new program.
Well, the bar on the far left on that chart, I mean, it wasn't zero because computer science has been around for a long time, and the IT program that we used to call it Computer Network Systems Administration, now we call it IT. They've been around for a long time.
Gotcha.
So,
okay.
yeah.
Right. There's
so it didn't go from 0 to 17.
Okay.
It went from 10 to 17 or something like that.
That's still a big jump.
Yeah.
That's cool.
It's. I think Michigan Tech has aspirations to grow. I don't know if you're aware of this, but we sort of have some numbers out there. We'd like to be at 10,000 students. We're 7,000, a little over 7,000 now. That's a good size. It's like what our dean likes to call the Goldilocks size. It's just big enough to be doing some important things, but small enough so that the students can still have interactions with faculty and so forth. But we think there will be more opportunities for us if we can bump up a little bit more and get up to 10,000. We're not doing it tomorrow. We're saying like by 2035, we'd like to get to 10,000. But we also believe that the College of Computing will be a driver for that growth. That's why that chart's interesting. That shows that if we get to 10,000 students and we're 25% of that, will be at 2,500 students, and that I would like to see that.
Yeah, that's great. Thank you.
Dan, good to see you.
Hi.
Paul, great presentation. I have one question for you, one question for Dan. So you talked about quantum computing, and you mentioned that right now we are in the hundreds of qubits level, but to actually achieve something we have to be in the millions level. What would you say are the major bottlenecks there, and what kind of breakthroughs we would need to reach that stage?
Yeah. So I think, so in terms of the bottlenecks for quantum computing, I think one of the main ones is error correction, coming up with efficient ways of doing error correction. Because I mentioned there's this sort of coherence time, like how long I can stay in that quantum state that we're trying to put it in. And what they tend to do to be able to do the error correction, they have a number of physical qubits, and you combine a number of those in one to make a logical qubit. And so right now, some of the algorithms, you need 1,000 logical qubits there's 1,000 physical qubits to make one logical qubit. And so then if you need, say, 1,000 qubits to do the operation, that brings you to that million of qubits. So there's ways to do error correction more efficiently, where you can reduce the number of physical qubits to logical qubits. That's an important thing. People are working, there's some promising algorithms that are coming along, so that's one of them. And then I think too is, there's just really, how do you, it's interesting, and people are working this too, but really the electronic control and readout, say for like superconducting qubits, there's a lot of control lines that have to come into these dilution refrigerators that are operating at millikelvin temperatures and getting those signal lines in and out. And right now what they do is they have banks of Keysight signal generators, and kind of getting those electronics reduced and getting them getting some of those electronics into the refrigerators and to reduce the amount of lines coming in and out of their refrigerator. I guess those are the two things that really kind of jump to mind, is in how you kind of scale and deal with getting more electronics closer to the qubits and not also destroying the quantum state of the qubit as well too.
Thank you. Dan, question for you. On the applied computing side, I saw bachelor's and master's program. Do you have any future plans for a PhD program anytime soon?
So right now, there's a university-wide program called Computational Science and Engineering. You might remember that. So we do not have a PhD program in my department, and for the most part, we're just kind of glomming onto that one. I mean, we're taking advantage of that one. And in fact, so Guy Himbroff?
Yeah.
Okay, so he's now the director of the CS&E program. His office is right next to mine, and so it's not a college of computing program. It's a campus-wide program, but we are using that in my department for the few students that we have that are interested in the PhD. Computer science still has CS has a PhD program. They've had it for years. So, but there are some things coming. Applied computing is kind of a funny name because it's not really a discipline. It's just kind of a catch-all name for my department. But things like cybersecurity, that's a discipline. So we might have someday a PhD in cybersecurity, or probably the most likely next one to come is a PhD in data science, because we are looking at forming a department of data science, and people can't decide if what comes first, the cart or the horse, but maybe we get the PhD in data science first, then we form the department, or the other way around. But those PhDs need to be named after a particular kind of discipline. I think that's the likely thing that's going to happen.
I think we have time for one more, if anyone has any additional.
Thank you for the great talk. I have a couple of questions. You can choose to answer any one of them. So first question I have is, we have many age-old algorithms which form the basis of a lot of systems today. Let's take an example of Fourier transform. So what do you think, do we have to make radical changes to these algorithms to implement them on quantum computers? So this is the first question. And second question, you kind of compared classical computing and quantum computing on the computing power they can give us, but are there any comparisons on how much power they require, like the wattage or things like that? Thank you.
Okay. So let's see. The first question again. So the first and second one was on the power, right? But what was the first question again? Sorry.
About some classical algorithms.
Oh, classical algorithms. Yeah. So I think. Yeah. So there's many things we typically do that we're not going to ever do with a quantum computer. The quantum computer is not going to just accelerate everything. There's certain types of problems that that's going to be good at solving, and there's other things that a classical computer is going to do much better. It is interesting, so one of the things, one of the big drivers, as I mentioned, was the breaking RSA encryption codes. Well, there are people right now making post-quantum encryption codes as well too, right? Codes that can't be broken by a quantum computer. So people are already thinking about, well, the quantum computer, and so there's people bringing algorithmics just using sort of classical computers that quantum computers can't get to as well too. So there's kind of a little bit of a race there between people coming up with other ways of doing classical algorithms versus the quantum computing as well too. So I don't think Yeah, so it's like I don't know if it makes sense to do a Fourier transform with a quantum computer. I don't think it really does. But sometimes, like, there's actually one of the reasons why quantum computing got going was Richard Feynman posited back in like early in the 1980s, I think, around. So at the same time I was programming that Sphero Univac, was that quantum computing could potentially solve very complex quantum mechanical problems, or say quantum physics, quantum chemistry types of problems by using the quantum physics to solve a problem that, sort of similar to what it was, the operations that are actually going on. So it's, I think, yeah, I don't know, there will be new algorithms, they're going to be algorithms, but I don't think you're trying to do the same type of algorithms. So that's the question I'll answer. So we can talk about the other one.
How about another round of applause for Dan and Paul?